Okie dokie. So we were talking about signals last time. Let's see. I think Emily had posted what she called a better picture of what I was. This is a better picture.
You can actually read it.
Well, it seems a little fuzzy.
Okay. A little fuzzy.
Perhaps it's a better picture, but it's not necessarily what I would call a good picture.
No.
Yeah. And look, they even they didn't even spell this right. You got this it's inter-process communication. You got this for a really janky site.
So there's 2 pictures unusual. It was this, and then yours that was confusing.
Well, okay, but mine said IPC on it.
That's why you take Dr. Lorenzo, you can't read it, you edit it.
Ready? Get a white box, put it over it, and then type in IPC.
That's what you want me to do?
You don't have to, I don't care.
Fine, I'm leaving it. All right, well, we're going to be talking about some of these today anyways. So in any case, this last class, and let me just go, I'll go back to a thing here. So we've been talking about signals. Shut up. All right, so we're talking about signals. So this is different ways that processes can communicate with each other. And we're going to talk about signals in more detail today, specifically with what are the primitives of them, and then also what are the limitations and how do we bypass the limitations. That's what we'll go into Emily's dumb picture here with the misspelled thing. So in any case, a signal is a way to sound an alarm along a certain list of known signal types. And let me give you that list. This guy give me my list of signals. Yeah, here we go. All right, so there's a whole bunch of signals that are built into the system here. The ones that are most common are like sig abort. Let's see. There's a sig pause, sig continue. Sig kill, sig interrupt. That's super common. Probably the sig interrupt along with the sig continue are very common ones. Sig kill. Okay, so now the important thing is that all processes already have a way of dealing with many of these signals. So for instance, if you send a sig kill to a particular process, and there's going to be 2 different ways of doing that we'll talk about here in a few minutes, but let's say I'm a running process, regardless of how I came to be, whether I'm somebody's child or I'm the parent process. If I receive a sig kill, even if I haven't registered myself to specifically locally deal with that, that process is going to die. Sig kill is kind of like the way of saying process die. Okay, so these are signals, known signals in the operating system that processes likely have already implemented, at least in some of these cases. Okay, sig interrupt would also pause a process by default. When we talk about signals, we're really saying, well, what if I want to handle a signal myself? What if I want to interject something in here? A reasonable way of looking at this would be if you've done any mobile application development, for instance, on Android, there are and iOS has the same thing. There are moments in time during the activity life cycle. I'm not going to bring that up here. This guy right here, when the programmer can choose to add in their own stuff associated with what's happening here. So as an Android programmer, when onCreate is called for an activity, I can choose to write my own version of onCreate, still call my parents' version of it, but then write some more specific stuff that's pertinent to my particular activity I'm writing. Same thing with onStart, onResume, onPause, onStop. There's all sorts of different moments in time. These are similar to how signals work. We can decide that we want to add some special responses to certain signals. All right. So now there's kind of two different ways for us to look at these signals. We see this giant list of signals, and I mentioned that a couple of these, like sig interrupt, is commonly used. Now, we can go ahead and hijack that and say, okay, I want to add something whenever sig interrupt is sent to this guy. But more than likely, based on what we've been talking about in here, we're not really looking at augmenting our processes to add some additional behavior to what it already knows how to do. We're talking about having the ability to kind of build our own custom communication into with signals, and they provide us kind of two user-defined signals here: sig user 1, sig user 2. So these are signals that will not already be implemented for a process, that are purely usable for the users, where we can say, look, this guy is something that I'm going to use, and there's no other default behavior for it. Okay. So here's our list of known signals, let's say, along with the two extra ones. And we'll come back and look at several of these at some point in time, because these guys are used in conjunction with some of the other interprocess communication stuff we're using. But we want to think about today, what are our limits of what a signal can do? What are the limitations, and what are the kind of the use cases, I guess. So for that, we're going to draw a picture. And I know I mentioned this last time, but I think the picture will help us follow this a little bit more. Okay, so in our examples we've been working with, we had our parent process. More recently, we had the parent create two children, right? Two child processes. So now we want to think about this world here. Who knows about who? Now, and I'm going to use the ones here with the arrow. The parent process knows about the child. Actually, you know what? I'm not going to use the one with the arrow because it's a two-way street there. Parent process knows about the child, and a child knows about their parent, right? Both sides know about that. Similarly, the parent knows about the other child, and the other child knows about their parent. But these children do not know about each other. Okay, they don't know about each other. So now we have to start thinking about, how do signals actually work? Two ways, I'm going to call this, to fire a signal. One is with the raise function. This sends a signal to the current process. The other is the kill function. This sends a signal to a process given its process ID. All right. So if we go back, and we'll experiment with these a little bit just to show how this works. We go back here, this parent could send a signal to this child because it knows that child's process ID. This child could send a signal to the parent because he knows the parent's process ID. The parent could send a signal to this child because it knows its process ID. This child could send a signal to the parent. He knows his process ID. But as we stand right now, this child cannot send a signal to this child because they don't know about each other's process IDs. That makes some sense? All right. So we want to ask the question, and that's what we're going to answer today based on Emily's bad picture. Intercommunication, what
It's the same spelling. If you look at it.
is ICP? So this guy took it from the same bad source on Google, because it's not Google, it's some stupid website on Google. But mine said IPC, didn't it?
Nope, it says ICP.
Really? I hate all of you. Well, it is inter-process communication. IPC is the correct acronym for that. What was I talking about? Oh yeah. How do we get the children to know about each other? That's our big question that we're going to attempt to answer today. All right. But before we get there, let's look at some ways of keeping track of these two things and looking at the two different functions. So I'm going to open up our code here. I already stored those couple of signals. Get rid of a couple of stuff. Okay, so what we're going to do is we're going to have a way for the parent to remember the two process IDs. All right, so we're going to create an array for the parent. So this is going to be int my children can hold two integers. All right. In my particular example here, I know I'm going to do something twice. So I'm going to create two child processes. And let me get rid of a bunch of these things here. So I'll create a child process. If I'm the child, for right now, I'll just do a printf. I am the child. And then he dies off. Else, if I'm the parent, I'm just going to go ahead and store the process ID of my child. Okay, because every single time that parent calls the fork process, he's going to get a new process ID. That makes sense? And that process ID will be the process ID of the child that was just created. Like in this picture, the first time fork is called, he'll get the process ID of this one. The second time he calls fork, he'll get the process ID of this one. I'm just going to store those two separate process IDs in this two bucket array. All right. So with that in mind, I also have to keep track of num children. So right now we have zero children. So if I'm the parent, I'm going to set my children at bucket num children equal to that process ID, the process ID of the child that was just created. And then I'll say num children plus plus, so that the next time around, I'll store in bucket 1, the child I just created. All right, just storing 2 integers. All right. And in both of these cases, if you're the child, you just, you wake up, you say I'm the child, and you die. In my current example, they're not doing a whole lot. All right, so now I'm not going to currently, well, I could say wait null. I'll just wait for the kids to exit. It's not going to kill anything. This waits for all children to finish, which is going to happen real quick here. All right, so I'm going to go ahead and do a little loop for int I is equal to 0, I is less than num children, I plus plus, and I'll do printf child PID %d my children at bucket I. And then maybe I'll sleep for 2 seconds. All right, so the current program goes through, creates 2 children, parent stores the process IDs of both of those children, and proves that it has successfully stored those 2 PIDs in the array by spitting them out to the screen. I am the child, missing semicolon. Yeah, I said I kind of had that when it gave me the completion options. I had num children, and the one was missing the n. I did this time. Oh, but at least I was consistent. Children. Hey, some folks might pronounce it that way, so just being multicultural. All right. So we see that a parent did successfully store the 2 different process IDs of the children here. Go ahead. Sure. So remember, the child's version of PID here, if I just put in PID, that's going to print out a 0 for both children. Because if you're the child, you get a process ID of 0 that lets you know that you were the clone. If you want to actually get the process ID of the child, you got to do get PID, call the function, and then also I could say, and my parent is %d get my parent's ID. All right, so I'm child 2483. My parent is 2479. I'm child 2484. My parent is 2479. And here's the 2 children from the parent's perspective. Go ahead.
Why did that happen?
Just how processors are scheduled. No, I don't. I have it waiting. Oh, I see what you're saying. Why did the parent print those things out when this child hadn't finished? The reality is we don't necessarily know that child hadn't finished. All we know is that the child does not finish until it actually finishes outputting the stuff on the screen, which is not the child process's job. When it entered the CPU, the reason that IO is expensive, well, we see that IO is expensive because every single time we print something, it slows the program way down because it actually has to leave the CPU. So the process got interrupted for it to go and do this. So my feeling is that it had gotten, since this was the last instruction, the child was interrupted but didn't die. Well, actually, the child was interrupted and did die, which then freed up the parent to print out the process IDs. but it didn't have, the child didn't happen to get their access to the output stream, standard output stream, until after the parent happened to get access to it. So I'm thinking more of a timing thing, because the operating system writing stuff out uses the syswrite system call, which is on the operating system, not on these processes. But it is an interesting question. If we run it multiple times, we might get different behaviors. Yeah, we did get a different behavior that time. This is the behavior you would have expected since we were waiting. Yeah, so. I wonder if we run it enough times, will we eventually get those first before both of the children say anything? I'll give it 3 more runs. I doubt that will happen. Okay. So in any case, we have proven here that the children, well, that the parent knows about the child process IDs. Okay, so that fills in, that proves what we have right here. The child knows about their parent, the child knows about themselves, but the child does not know about the other children. And if I go through and I try to print out the values of my children inside the child, we have access to that variable, but that variable hasn't been filled up with values. It's going to be the default value of probably a bunch of zeros, not because PID is 0 for the child, but because that's what the default value typically is for integers. So we have no way currently of getting that information to the children. And we're going to look at fixing that today after we look at signals. All right, so what we're going to do is we're going to register a signal. All right, so to register a signal, let's steal this here. If I'm the child, I'm going to go ahead and I'm going to register. Well, here, I'll just stick with the actual signals here. I'm going to register SIG USR1. That was the user defined signal. That one doesn't have any built-in functionality. Realistically, though, I can put any signal in here that I want. I could just decide, okay, I'm going to hijack the SIG interrupt and just kind of put my own code in there for handling that rather than use the default code. But SIG user 1 and SIG user 2, we know those aren't going to be predefined. I'm not going to be breaking something that might be an important functionality of how processes work, something like that. Okay, so this is the child saying, I want to register myself with this signal, and I want the handler to be, I call that SIG catch func, that function. All right, so we wrote a function up here that returns nothing called SIG catch func, and it takes in an integer as a parameter. That integer is the signal that it caught. Because you could register a process with multiple signals and have the same handler for all of those signals. That's allowed. Or you can say, I'm going to have 5 different signal handlers for 5 different signals, and I'll create signal handlers for, well, I'll link my signals to those different handlers. You can decide how you want to write your logic. But we're just looking at a single signal thing here. All right, so the children will register themselves with that. And what I'm going to do here is I'm going to move that print statement into that signal catch func. I'll tell the child to go ahead and go to sleep for 2 seconds. mostly to ensure that they have fully registered themselves with the signal handler. I don't believe this function here is what's called atomic, which means it happens in exactly, or as if it happened in exactly one CPU cycle. So if I immediately call the raise function right afterwards, I think there is a possibility that we might try to raise a signal before it's fully been registered with the operating system. I think that's possible in that case. So just to drive the point home of what we're trying to accomplish today, I'll go ahead and just tell it to sleep for a couple of seconds. All right. So now looking back here at the slides, I said there's two ways of firing a signal. One is the raise function, one is the kill function. The raise function is a local only thing, and we're going to see that here in a second. Since we're spawning two children here, and each child raises the SIG user one thing after 2 seconds, presumably both children have already been created before either one of them raises that signal for the first time. Make sense? The two children both exist before either one of them tries to raise the signal. I'm giving it 2 seconds. Things aren't going to take that long on the operating system. That's not the point of what we're talking about here, but we can all agree that both children exist before either one tries to raise the signal. So what we want to see here, what we want to observe is when one of the children raises the SIG user one, do they both respond to that? Or does only one of the children respond? That is the local child. So one of two things is going to happen here. I'm going to get this message twice, or I'm going to get that message 4 times for each of the raises. So do these children, do they accidentally know about each other through the raise function? Is the question we're asking. All right. Now we've advertised that they won't, because raise sends a signal only to the current process. All right. So we'll go ahead and run this guy. We expect to see only 2 calls here. So here's the first child calling themselves. Here's the second child calling themselves. And we can actually steal this right before we raise. We'll go ahead and have the child scream their process ID and say that they're raising a signal. So we'll get four lines here. So I am child 94 raising signal now. I am child 94. My parent is 90. So this is the receive signal. In fact, let's put that up here. And I'll go ahead and just print out whatever signal the catch function received. We'll see the numeric version of SIG user one. So 4442 is raising signal now. 4442 received the signal 10. 4443 raising signal now. 4443 signal received number 10. Make sense? So raise only communicates to the current process. It does not allow the children to accidentally communicate with each other by raising the signal. Even though they don't know about each other's process IDs, they don't have those values, they still presumably may have been able to kind of shoot the flare up in the sky and both children see it. Not the case. Rays only send something to the current process. Now, an interesting question here, though, would be this. Why call rays? But I can actually just call that local function. We got the same output, didn't we? What's the benefit of using the raise function here as opposed to just calling the function directly? Is there any benefit in this current case, what I'm doing? Certainly the output doesn't indicate that there is, right? So if all I'm doing is allowing the current child to, if I'm not relying on the operating system itself to get any information, and all I'm doing is relying on the current child to get a signal called, I don't even need to register themselves with a signal. I can just call this function whenever I would want to call that function. But if we go back to this picture, there is something else at play here. Oh, send to back. That's the operating system. The operating system knows about everything. It knows about all those things. And when you use the signal subsystem to raise a signal, that is noticed by the operating system. For example, logging, automatic system logs at the operating system level. This is probably going to be the most obvious example. It will log whenever there's errors and things like that for debugging purposes. It'll log when signals are raised. It won't necessarily log when functions are called. Make sense? So if we happen to be doing something that we want the operating system to also be aware of, we might use raise in that particular case as opposed to just calling a function. Because now we're actually utilizing the operating system to go back to this process. The operating system is who's actually raising the signal. And they're just targeting the current process. Presumably, they're going to be using the kill instruction. And we're going to see that here in a second. All right, so any questions here about how raise works? Raise effectively is self-talk, right? A child can talk to themselves through the raise function, and I suppose it's a little bit of I don't know, they're getting the operating system involved and screaming at them so they can the OS can scream at the child. The alternative to raise so I'll just comment that out for a second here. And what I'm going to do is I'm just going to have the child just sit there forever and wait. All right, I can do small sleeps in there if I want to, but I won't. I'll just say, while one, do nothing. That's what that's doing. All right. So presumably we never get to this line. All right, so when a child comes into existence, he registers themselves with a signal and then starts waiting indefinitely. We've already proven that the parent knows about the two children. All right. This is going to make sense with the kill command here. So the parent, I'm going to say I am the parent. Child PID, yada, 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 prepare to die. The parent will then use the kill command, targeting the current child with the signal they want to raise. What I'm going to do is I'm actually just going to flip flop these things a little bit. We'll have the parent hang out for a couple of seconds before they start killing off the kids. The parent will then, after they've raised the signal to all the children, will wait around for the children to finish dying. That will just say all the children are dead, parent exiting. All right. Now remember, the child here is sitting here in an infinite loop. So if I want the child to actually die, I'm just going to go ahead and call the exit system call with a return value of 0. That will kill off this process, undoing that infinite loop effectively. It immediately kills the process, as opposed to a return 0, which would just bounce back and have us sitting here in the busy wait loop. All right, so both children come into existence, they register themselves with a signal, and then they sit and wait forever. The parent, after creating 2 children, sleeps for 2 seconds, goes through the list of their process IDs for their children, warns the world that I'm about to shoot my kid. You know, this is one of those situations people are walking by. I think I told you that I was at breakfast one time talking about this. That was pretty interesting. Then the parent will use the kill command. Now, don't confuse this with what the signal is actually doing. This is the system function for sending a certain PID some signal. It does not have to be the kill signal. It's maybe even an unfortunate name for the I don't know, the system call. Modernly, we would probably just have 2 different versions of raise. If we were writing this today, we'd have raise that takes no parameters, that just sends a signal to the current process, or raise that takes 2 parameters. Well, one that takes 1 parameter that sends a specific signal to the current process, one that takes 2 parameters that sends a certain signal to the given process. That's probably how we would write it today. But they didn't do that. It's called the kill command. So we're going to send this process ID, this signal. All right, so I'm the parent. Child, prepare to die. I'm the parent. Child, prepare to die. I'm the child, receive signal 10. I'm the child, receive signal 10. All my children are dead, parent exiting. Okay, so now we have a situation where it is the parent sending the signal to the child, this parent sending the signal to the child, and then this child dying off as a result of that signal. Why is it dying off? Because we said this in the handler. We exited in the handler. Go ahead. All right. So questions about that? We got a handle on what the kill and the raise functions do? Okay. Let me just do one separate thing here. Actually, I don't even need a return. I'll just get rid of that for a second. And then this is probably going to give us some warnings that this is unreachable code, but that's okay. So now I'm just going to I'm going to try to kill the kids over and over again, sending that signal to the kids, because I'm going to do that forever. But I've changed my handler to no longer exit. Let me just go ahead and stop this. Oh, you're not going to show me what was the killing me. Are you serious? All right, well, we'll watch it again then. Maybe I can scroll some with that. Hold it. All right, we definitely see that the child is responding. You see the child is intermixing in there. All right, so this child is receiving that signal over and over and over again, right? Because the child is not actually dying off. They're just sitting there in existence forever and ever and ever, just twiddling their thumbs, doing nothing. But the parent is forever sending the kill command to their child, just raising this function. But understand that this is effectively a parent process telling a child process to do something after they were born. So that's interprocess communication, right? We haven't just created a child process. Now the parent is sending a piece of information to the child process. Let's go the other direction. If I'm the child, if I'm the parent, it's not going to hurt to do it twice, but the parent could one time register themselves with that signal, but that means all the children will, no, they wouldn't. It's actually going to be an interesting thing to look at. So I'll use SIG user 2 for this one. So we're going to show the two-way communication where the parent can send a message to the child, raise a signal target at the child. The child can also send a message back to the parent, raising a signal. They could be the same signal, but I'll use a separate signal, SIG user 2. So I went ahead and had the parent register their process ID with this signal. This is before any of the children were born. And then the child up here, when they receive their function, they're going to go ahead and send the kill to their parents' process ID. So when the parent receives the signal or the child receives the signal, they'll print something out and then send a signal back to their parent, which should have their parent call this function. And then we'll go ahead and just have the child exit. And I'll go ahead and move that outside of, so this only happens twice. So the parent will communicate with each child. The child will receive the signal and then will communicate with the parent by raising a signal to the parent. The parent's going to have their version of the parent func. I got to make sure I registered parent func with the other one. I didn't. When I registered SIG user 2, I need to make sure I'm calling that other function. I could have called the function I was, but then it wouldn't have looked like a separate response, a separate thing. All right. So the parent's going through their for loop, warning the kid you're about to die. The child receives the two signals, prints it out, and then the child sends a signal back to the parent. The parent receives both of those, and then the parent waits for all the children to die, which happened, and then the parent exited. So that's two-way communication. Make sense? All right, so what I'm going to do here is I'm going to copy that. So there's an example of two-way signal communication. Through that in Slack. All right. So we still have the issue here of parent can talk to each of their children. The children can talk directly to the parent, but the children cannot talk to each other. We understand the conundrum. All right. Now, this is only a conundrum if we're solving a problem where it would be beneficial for the children to be able to talk to each other. So we need to create some way for these children to become aware of each other, aware of all the process IDs that are being involved here. So here's Emily's bad picture. And that's not how you spell shared either. Isn't that shard memory? Okay, now it's got one up on mine.
It's not even spelled memory right.
Ah! That's two up on mine. Convocation? What about indirect convocation? Okay, so really you didn't even present a different graphic. Truly.
Look at the green one.
That's not how it says. It says message quests.
Are they both that bad?
Yeah, they're both that bad. This one has the
Direct convocation, indirect convocation. Pipes and FIFO. Oh, and message passing. That should be IPC. That is pretty bad. Although I tell you what, when it comes to like cheating on exams, it's almost always like that though. Like the students that cheat, you get the same wrong answer from all the students, and it's like there's no way you would have come up with that on your own multiple times. Like sometimes you could have two correct answers that look shockingly similar, but if there's not too many ways of writing it, maybe you just happen to pick reasonable variable names. Will you have the same dumb mistake? So that was pretty funny. All right. So what we need to do is we need to look at, of course, shard mem or shared memory is what we're going to look at. So this is a place in memory that exists outside of the local memory space allotted two T's, allotted for a process that allows multiple processes in the know to access that memory and share information. All right, so this is a two-step process. One is we need to create shared memory and receive the ID associated with that memory. The second is to attach to the shared memory given its ID. Okay. So what I'm going to do here is I'm going to create a I'll just write it in here. It's fine. All right, so the system call for getting shared memory is something called SHM get. So I'll put that in here. Shared memory get function. All right, so this is in sys shared memory. So I'll go ahead and bring this into our code. And what we do is we give it a key, we give it the amount of shared memory, and we give it a flag. The flags that are possible to put in there are these guys. IPC create, this is the one we're going to be using. Okay, create either creates new shared memory and gives you the ID of it, or it will return the ID of memory that had already been created given the same key. So when I said in the know, all processes that want to share this shared memory have to know the key that that you're using. All right, so I'm gonna steal a couple of things here. And then we'll talk through them in I don't think I'm using this in my code. All right, and I already have buff size up here. All right. The who? Oh, you want all the new stuff? Okay. I'm going to be adding more stuff. Okay, you just want to catch up.
Yeah, it's what it's.
All right, so I create a structure here called shared memory segment. That's going to keep some information about my shared memory, and we'll see this here in a few minutes. But the most important thing here is that I'm going to have a string. So I have 1,024 bytes. 1,024. A char is of size 1 byte in C. So it doesn't matter what you do here. It's memory is memory. We're just labeling it with a type so that if we were to walk through that memory, it would take the appropriate size steps. All right, and we'll see some examples of that as I start messing with it. But in any case, this structure is holding some information about the shared memory that we're going to create. We're going to see this here in a second. So that's what a shared memory segment is, the struct thing that we created. And you can call this guy whatever you want. It doesn't matter. So this is just holding on to 3 pieces of information, 2 integers and a string. And this string is of buff size. Buff typically stands for buffer, just kind of naming convention. So this is going to be something capable of holding 1,024 chars. For no good reason other than I'm creating shared memory of that size. All right, so line 39 here, I go ahead and just create a variable of type shared memory segment. I have a struct. Haven't put anything in that struct yet, but I have a struct. All right, then I'm going to go ahead and give myself a pointer to the buffer. Now, this is just a variable capable of holding a memory address. It also does not have a memory address yet. All right, but it's capable of holding the address of a char. So now I mentioned there's a 2-step process for getting shared memory. Okay, we get the shared memory, and then we have to attach to it. Now I did have a key up here, didn't I? So up here, my shared memory key I created, just hexadecimal value 1234. You make it up. So all of my processes are going to know that hex 1234 is my super secret key for my shared memory in this case. Make sense? They're in the know. So I'm going to go ahead and ask the operating system with a system call for the ID associated with the shared memory with this key. Now, just to show you back in here, shared memory get. This takes in the key, the size of the shared memory, and I'm going to pass it. So realistically, what my shared memory in this case is going to be the size of that struct, which is big enough to hold 2 ints and 1,024 byte char array. It doesn't have to be a struct. I can just say, hey, give me a bunch of bytes. Give me 2,000 bytes and I'll be happy. You can decide what you're going to store there. All right. Now, this last thing was the flag, and I'm actually going to ultimately just leave it with that, but we're going to talk about this here for a second. The last thing is the flag. Now, typically when you see things like that, some number like 0644, we're probably talking about permissions for that memory. So this is the 6 would be read and write access for the owner. And then the 4 and the 4 would be read access for the group and everyone else. All right, we're not going to care about that in this particular case. We'll just let it be default permissions. But the reason I put that in here is notice this vertical bar here. What is this actually doing? This is something you probably have learned from me at some point, but you also would have done it in 325. What is the single vertical bar in C? What does that represent? Go ahead. Okay, what kind of OR? A normal OR is 2 vertical bars, just like a normal AND is 2 ampersands. What's a single vertical bar? Nope, exclusive. Anybody know what the exclusive OR symbol is? Yeah, that dude, that's exclusive OR. So what's a single bar? Bitwise OR. Okay, and when I say bitwise OR, we're actually dealing with it on a per bit basis. So we're going to take this value and represent it in binary. We're going to take whatever this value is, IPC create. That's when you see stuff in all caps like that, it's probably a constant, or actually what's called a macro in C, which is just a hard-coded value that holds some number in this case. All right, so I'm taking the 0644 in binary and whatever number IPC create is, I'm going to bitwise OR them together, giving me a new result. Now, at the high level, we might say, okay, well, fine, that's just some other number. What the heck does that mean? What's actually, and this is a pretty common thing to do in older C system call stuff, this is called masking. So we're taking the multiple permissions that we might want to have associated with something, and you don't just see it in system calls, you actually see it quite a bit in Objective-C, even in some newer languages when you have to create something that has multiple permissions associated with it, rather than you having to just pick one of 5 different permission things. You might want to say, well, it needs to have network access plus this and plus something else. So I'm just going to go ahead and OR those guys all together, and the resulting value will be unique and basically means all 3 of those guys. Make sense? So that's what's going on there. I'm gonna just peel it away and keep it simple. Say, we're gonna create that, as opposed to create it with a specific permission. We'll just deal with the default permission unless we get something that we're not happy with, and then we might go back. But I think the default permission is going to be acceptable for what we're gonna do here. In fact, well, no, I want to use it in a struct that might be helpful in where we're going with the homework. All right, so I will get the ID associated with my shared memory, either for the first time or forever. You know, if it's already been created. Then I need to attach to that guy. I'm going to skip my error checking as usual. Now, I'm not moving this stuff inside the, actually, you know what, I'm going to now, just because we're dealing with this at, so I'm going to have the child get the shared memory ID. I'm also going to have the parent get the shared memory ID. Both of them are going to get the ID of that shared memory. It should be the same ID. So we could have actually just gotten it one time. In fact, I'll go ahead and say printf. That stuff. All right, so I'm not using any of the signal handlers right now. I'm still registering with it. So I can even take that out. All I'm doing is getting the shared memory ID and then printing it out from the child's perspective. So 2 different children should have that. And then the parent should print it out twice as well. And we'll see what those IDs look like. Hold on a second. Give me a moment. Seems very unlikely that I would have gotten a 0. But it is the first time I'm asking for shared memory. Okay, well, whatever. All right, so now I'm going to go ahead and I'm going to attach to that shared memory. On both the child side and the parent side. That's my pointer to my struct. And then I'm going to go ahead and have the parent sleep. Actually, I can't have the parent sleep there. I'll have the parent sleep here. Just for the example of this as well. I'm going to have the parent sleep for 1 second before we spin back up. The child will grab the shared memory, and at that place we have a counter. I'm just going to use the counter for a moment. Current count, %D, star. So I'll print out the count. Then I'll increment the count. Then I'll print it out again. And here I'm going to put the process ID in here as well. Yeah, it's not getting the. I thought the 0 seemed too good to be true. Shared memory get is not getting an actual place in shared memory. It's dying actually right there. That's why we're never seeing current count. If I put a 5 in here or something like that. it's also dying there. When I try to access the shared memory is where it's dying right now. Wonder if that's a online GDB thing, if they're not supporting shared memory. Well, either way, I'll figure it out. So presumably we get the idea of our shared memory. We're able to attach to that shared memory. And then we're able to, what I'm trying to do up here is I'm printing out the shared memory ID, which I expect to be an actual number, not a 0. Then I'm showing what the current value, well, my intention is to show the current value of count from this struct. And then I want to increment that count in that struct. And I'm presuming I'm incrementing the count in that shared memory. 1 second later, the parent will release, creating the second child. Second child will attach to the same shared memory. We'll read in the count. This time the count should be a 1. Start off as a 0. The first child incremented it to a 1. The second child should read in and see, oh, it's a 1. Change it to a 2. And then maybe down on the parent side, the parent should be able to read that shared memory and see that it's a 2. Change it to whatever they want, but proving that all 3 processes are able to share information in that one place in shared memory. All right, so before Thursday, I'll figure out what online GDB wants for shared memory, or if they maybe don't support it, or if we need to do something special. But all this code is the correct code outside of we're not getting a real shared memory ID. That's why it's not working. Okay. And then once I have that working for you, we're going to, and you can play around with it if you want, but then we're going to have a assignment that's going to have us do something with the children communicating with each other through something other than a file. Remember last time we were looking at having to do this like weird timing things with files, not maybe the best thing to do. All right, questions, comments, concerns, bribes. All right, I will see everybody on Thursday.